Okay, so I have got the basics of geometry down, basically. Took me quite a while. I will say that if something's missing, just scream at me in the comments or, email me because it's been like 6 years since I did geometry. Yeah, that long. And all the documentation is in my head, kind of in my head. So basically, I don't have all I didn't know the documentation before I did them. Basically, all these documentations are redone by me because it's been 6 years. I don't remember them. So it might not be the standard way that you learned it in class because, well, my division. So it might be completely different than, a textbook, another textbook because, woohoo, I don't remember 6 years ago. So yeah, anyways, first thing I said was vector array. I don't consider this a fucking array because array is such a weird nerd. So I call it vector instead because vector is way more useful and we actually use it. Now, line is also definition, and then these definitions are on the side. I mean, I talked about them like 300 times, so I don't think I need to spend it more time. But sure, segments are lines. I don't. I mean, at at a certain point, I never knew the def. I mean, I knew the difference between a segment and line, but what's the point of defining them any different? I just said there isn't. So. hmm. Not really that important. Then the symbol 90 degrees. That one's more useful. This one's way more useful. Triangle is total degrees 180 is totally a needed necessity with my proofs. So take it. Reflective property. Eh, reflection. I don't know. No, it's not reflective property. It's reflection. I don't know why. Yeah. As you can see, I have never used some of these things since uh, high school. And in college, no, I haven't used them in college at all. And uh, I'm going, I mean, what? I don't know. I don't know. And some of them are just from my memory, like the reflections definitely need there's something, and I'm basically saying like some of them are not useful. Anyway, obviously these are useful. Radians are a keystone. That is useful. Degrees, I'm not sure. I mean, it's more intuitive for sure. I guess it's more is useful. So yeah, sure. Radians and degrees are useful. Um, so in that sense, but this definitely is not useful. Knowing what is acute, obtuse, and right angle, yeah, sure. But I never seen the word acute or obtuse ever used after high school. As you can see, a lot of these things are like shorten down because I don't find them useful. Uh, if they're not useful, I kind of like forgot about it and said, "Oh, I spent like 3 hours in Khan Academy, doing these totally legit useful things that I just put. What is this triangle? A cute triangle. Oh, what is this? Basically. But it's completely useless. I haven't heard of proof that needed to use acute triangle or obtuse triangle. I don't really know why they even gave me that. But Equado isosceles and scaling. So isosceles, I think I use. Equado, yeah. Scaling, yes. So yeah, but I haven't used the wording of that. So, but yeah, sure. Yeah, they're kind of useful. Yeah. So, but identifying what is equilateral isosceles and scaling, you don't need to identify scaling because it's kind of like obvious. Uh, but isosceles, yeah, sure. There's some questions that I've done in statics that use that triangle. Equilateral, yes, in statics. Yeah. Yeah, I'm just pissed about the acute and obtuse and the reflection because I spent so much time in Card Academy on it. Like, why the hell is that useful? I'm so pissed on that stuff. Like, you'll see a few things in geometry that just pisses me off a little bit. Um, Adjacent angles, okay? So, god damn. I forgot about the wording of adjacent, but I know what they are, and it's such a basic thing that basically if there's two angles that are attached to each other, with a common line, I guess. I know ray according to geometry is ray, so ray. Yeah. And then there's supplementary and complementary adjacent, and that I have used in statics. Definitely have. Uh, a few of the questions, statics. I have, yeah, it's up there, some of the books. If you want me to give you a question on that, I can. Anyways, I haven't used it as you know, equations. Like I haven't seen like 2x plus 6 and 15 plus x plus 4 as an equation, but I have definitely used the idea that the angles are the same. There's two lines like this in statics before. Have I used it anywhere else in statics? No, 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 no. But I have statics is a very key point, like used everywhere. So yeah, it's very useful, I think. Um, yeah, so if we move on to planes and lines, and definitely have used this over here. Uh, then we go to the useless stuff. Rotations and translations and weird ass stuff that I never used. Uh, but I put it here because it's in geometry, like rotating and dilating down. To be clear, I have never used it after geometry, like this stuff, like what, why? I've never used it. But here's another triangle. Bisectors, yeah, I have seen this in statics again. Um, Convective poly, I mean, yeah, that's kind of everywhere. So convective and concave. And here's another brain teaser, I guess. And then perpendicular parallel lines obviously is used. Um, and I forgot about postulates because that's an assumption that is accepted without any proof. I believe there's five postulates in whatever book. I forgot what the book is called. Somewhere over there, probably. Uh, Yeah. Euler's book of something, right? Oh God. Yeah, I mean, eh. Somewhere there. Go ahead and search my room. Don't do that actually. You will get 911 called on your ass. Um, anyway, area I define it in calculus because it's the easiest way to define something, and I'm not. And here's the thing: there's some geometries that I'm not willing to do without calculus, and I'm just gonna leave it out there. Basically, I'm not gonna even touch it unless it's calculus. Yeah, same with volume. Some volume weird shit I'm not doing without calculus. And basically, you're gonna see that later on. Because I remember in geometry, you're just given some formula and just have to plug and chuck. No, not here. We're just gonna put that in calculus, and we're just gonna teach you that in calculus, not here. Yeah. Basically, is what we're gonna plan to do. Polygons and quadrilateral triangles, like there's four sides of a polygon. Yeah, that's obvious. Parallelogram, basically, let me just, yeah, as you can see, I don't have my good mic here, so yeah, my voice is shit right now. Anyways, we have a parallelogram, like this, basically saying that, that's basically what's happening. My voice is shit because I haven't got my mic on. Anyways, with that said, we have a rectangle, which I'm just going to give you the area. Um, oops. I pressed something. I pressed that thing. Very bad, not bad thing, but yeah. Here I'm making a list of like rapid fire things because it's kind of like definition. So why we're gonna give you this thing is because there's no, I mean, it's kind of, it's intuitive, yes, but I mean, if you want to define it in calculus, it's basically doing um, A, B in rectangle form, C, D. They're all constants. And then you do 1 dx dy, and that will equal the area of a rectangle. There you go. But we're not doing that. So it'll be 0 to B and 0 to H actually. But yeah, that's how I would actually define it. But we're just gonna give it as given because it's something that you can't really derive, but it's gonna be used a lot. Rhombus is this. Have I? Oh my God, did I give you guys any rhombus questions? Oh, did I give you any rhombus questions? Did I solve any? I don't think I did. Did I? It's probably gonna be in the proof area if I ever did it. But I don't think I did. So then there's a square, there's a trapezoid. I definitely proved the trapezoid because of the parallel lines. To be honest with you, sure, but yeah, sure, perpendicular lines, and therefore. They're basically just definition at the point. Triangles that, similarities that. I forgot to put congruent. That's fine. I'll explain congruent later. Additional property is this. We kind of know what that is. Subtraction property is this. Multiplication property is that. Division property is this. Substitution property is this. I'm just saying this because you kind of know this from algebra, so. Refractive property is the first time we actually have something different, which is basically claiming itself AB equal AB, and it's just for proof. It's a hearsay thing, in my opinion. Anyway, the midpoint is the middle of a segment, like defining segment, the middle of it, basically is what's happening. Uh, we already talked about this obtuse and cute shenanigans. If two parallel lines are cut by a line that the corresponding angle are congruent, aka fuck. I'm gonna have to explain congruency. I'm just gonna put it here because I'm not about to write another another painful congruent. Did I spell that right? Did I spell that congruent right? I think I did. Yes, I did. Okay, so congruent just means equal. And congruent is more powerful than similar, so I'll put that in first. Base. Yeah, and that makes more sense to me. Um, anyways, congruent, aka yeah. So if two lines from congruent adjacent angle, then the lines are perpendicular. Uh, in fuck. So congruent is a geometric way of saying equal, basically, but you're gonna see me flip-flop from congruent to equal because I don't care. Genuinely do not care. So because they're very much the same, basically the same. I don't know why they want to do I mean, I know why. It's just a definition thing, but basically I flip-flop because and then why did not be consistent? You'll see why later on. And the vertex is the corner of a polygon. Each polygon is the endpoint common to its sides. Anyways, vertex of isosceles is a weird thing because there's a base angle on the two sides that are equal, and whatever, it doesn't really matter. Um, technically that's a weird thing. Anyway, as you know, we have volume afterwards. So first off, we start with a triangle, basically. And basically what I say here is basically you get a rectangle, and you see that there's dividing by half to get a triangle of anything. So basically, this is our definition for the rectangle, basically. And then we get the Pythagorean theorem, but in reality, it's not made by Pythagoras. It's been discovered a long time ago in Egypt and Babylon. Do we know who actually did it? No. Some people called Impa. I forgot. I don't know how to say his name, but he didn't actually discover it technically, because it was discovered way earlier than him. Stolen value, right? A lot of things from Islamic culture, Middle Eastern and African and Asian and everything is like wiped clean in our names of them. Instead, they're pretty much all given to white people. Anyways, not made by this white guy. Basically, is what I'm saying. And then we get the right triangle here and 3, 4, 5 triangle. Basically, we just explained for that. And then we go to sine, cosine. Again, these sine and cosines are made probably by the Islamics and Indian people, not by a white guy. Um, I don't know. I'm not sure if they're named by whatever. It doesn't matter. Anyway, you kind of see what happened over here. You kind of see over here. And finally, I give you a unit circle, basically. Um, Pythagorean theorem, it's probably Islamic culture that made it. Yeah, basically. And then we proved it here, basically, if you want to read it. But I already did it a long time ago, so that's why I'm kind of skipping through it. But if you want to know, let me just explain what I did. Did I explain it really good last time? I don't know. Basically, we know that this sine is adjacent over hypotenuse, so it's a over c sine theta, and then it's cosine. No, that's what the fuck? What the actual hell? I got this wrong. What was that? Was I drinking crack or something? That is B over C. This is A over C. How did I not see that? How the hell? Um, excuse me for my vulgar language, but I am pissed off myself. Okay. Okay, I'm just gonna do something really cheeky then. And as you can see, I use different formats when I was in high school because I'm an idiot. That way I can change this back to A and B because it makes life easier later on. Wow. How the hell did I not catch that a long time ago? Oh well, anyways, oh my God, thank God I checked that thanks to you this video I'm making here. Anyways, a squared minus b squared, divide everything by c, and this equals 1. And basically substitute sine and cosine, and you're good. Oh my God, I'm very distraught by that. Oh, shit. How many dumb mistakes have I made? Also, if I make a dumb mistake, just please comment it or just email me and rage bait, whatever. I don't care. I can be as mean as possible for my mistakes, and I wouldn't really care. Um. Anyways, basically, then you substitute here this, and then you substitute here this, and then you get this form over here, which is our Pythagorean theorem, which is not created by that guy, but we're gonna call it Pythagorean identity for no reason at all. And then we play a little game here, where if we get sine of we get the A over here, we want sine and cosine. We can actually solve it like this. And why I like this is because I don't really like number question. I like proof-based questions a lot more because no, for explanations. Do I like it on a test? Hell no, because it takes forever, and then if I get it wrong, it's kind of hard to tell if I got it wrong. It's like good luck. I was like, yeah, I'm not gonna get the question right, am I? Is what I say every time I felt that. Anyways, AA is similar, and also congruence means similar. So basically, if this is congruence, you could get similar. Anyways, um, basically. Now, here's a bunch of proof, but I explain each and every one in a separate video that I'm not interested in doing the proofs like this one. You can look at the previous video if you want. It took forever to do that. And I already did the video on log, cosine, log, sine, so you can look at that too. Only thing I did is change the structure of it. Did I explain Yes, I did, long time ago. I did this, and I always don't like this, but I did this because it was in my study guide. For some reason, it was in my fucking engineering study guide for my FE exam. So I said I'll derive it. They didn't even derive it. I just had to derive it. Again, this guy did not do geometry since freaking high school freshman year, and I drive everything again. It was painful. Luckily, there's some memory of that floating in my head because I'm not sure if I can say his name, but my geometric teacher was very thorough and very proof heavy. So I kind of knew how to do it, even if I didn't remember it. He taught me a lot um, in geometry. and Herman's formula. And you can look at this painful, nonsensical non-nightmare, but we already did that previous video, so I'm just gonna skip it. And we already did the proof on this one too. And yeah, vectors is interesting. Um, I've I've uh I've showed a little bit of it, but I'm starting to realize that this should probably be in trig territory. Of cosine, left side, basically. But yeah, I put it in there. Uh, what's happening is that you get a this is a 4, 5, 3 triangle, so you're trying to get arctan over here, and then you're just splitting this into two parts, and then splitting this into two parts. And then you're adding it all up to get this formula to there. Basically, is what happening. Same with law of sine, life cosine, sorry. Basically, that's all we're doing. Um, I should probably move this into the freaking trig, not this section. I should get rid of it. I'm thinking of doing that when I get my trig ready. I'm still not ready with my trig, so. Anyways, the first time we have our new stuff is our regular polygon, where I didn't explain how to get the area of a regular polygon or angle of a regular paragraph. So that's what we're doing here, and that's what the painful nonsense we're doing here. And my eyes are sleepy because we are at 2:11 p.m. Yoo-hoo, we're late to my bed. I need to get to my bed so badly, man. Anyways. Over here, I divide this by half. I do L divided by 2. And from that, I understand this is a Pythagorean theorem. So I get this. I told you Pythagorean theorem would be everywhere. From geometry, all I remember from freshman, Pythagorean theorem, Pythagorean theorem, Pythagorean theorem, everywhere. And you just get the painful nonsense called fucking Pythagorean theorem everywhere. It's so much fun to do. Pythagorean, and yeah, so much fun. Yeah. Anyways, it is fun. I just, we had to get the H. We just get the H over here, and then we put H over here to get this form. Now, fun fact, I'm pretty sure this is not how my teacher in high school did it. I'm pretty sure he had some weird sine cosine method. No, not that. Some other method to figure this out. I don't remember it, so this is my re-derived version of it. Yeah. Anyway, I don't care. My way works. So that's the way I'm showing it. If someone shows a better way, I'll delete it and change it to that way. But so far, my way works. My way works. That's all I'm saying from that because uh yeah. Yeah, clearly I have a problem with remembering the way that my teacher did it. But yeah, here's another derivation I did. Basically, I divided by 3 and got this and basically did a triangle everywhere. Basically, after I got this, I split it into 5 groups because I got the bisect I wanted, and I made this into the same format, and then I got L divided by 2 over here. And I instead of using the Pythagorean theorem, I just said, let's just use arc, a tangent, and we have H on the top, which is going to be H and L divided by 2. Therefore, I got this format over here. And then I know H triangles like this, so I plugged H into the triangle version to get this. And then I knew there's 5 of them, and so I did this. And then all the other ones is like basically the same way. Why I did that way? It probably is the easier way. I learned geometry, but I forgot. Again, this guy forgot how to do the standard way, so I re-derived it to this way. So. Yay! I'm just gonna say that it works, so I don't care. Um, and then we did the trapezoid again. I'm pretty sure actually that's the same way as the teacher did it. So yay! Okay, so we got something that's the same. Anyways, and then the parallelogram, I'm pretty sure that's the same. Fun fact: this is the reason why a prism, because a prism is a 3D extension of it. If you were to get the volume of it. Of a 3D extension like this. The same thing where you just multiply by the what's this going to call W, I guess, because this is called the base B. If you're going to look at the volume of it, it's just multiplied by W because of the same reasoning. If it's a parallelogram prism. Anyways, I didn't really do that here, but yeah, whatever. A bunch of proofs that I explained in a different video, so I'm not redoing that. You can go back. You can go back to torture yourself on that. Um, yeah, because fun fact, I could do more proofs, but I don't remember any of the other proofs that I could possibly do. I might email my high school teacher to tell me more about the proof, but or I can look through all these textbooks I have. Yeah, I'm gonna look through these textbooks instead because I do not want to bother him, especially since it's summer vacation. I'm not wasting my time on that. Now we're going to circles. The first thing I'll say is the definition here is chord, secant, and then tangent. And from visual scan, you can kind of know. Actually, I wrote it here. A segment that is inside a circle and touches the edge. A segment that is inside a circle and intersects. What the fuck did I write here? A line, first of all. That is that cross through a circle. Yeah, that is literally the fish. What the hell was I thinking? Anyways, thank God for this. And then yeah. And then we got diameter, which is this, and we got the radius, which is that, and then we got the tangent, which is 9 degrees like that. Uh, which is pretty good. Thank God I caught that. Another proof here, just because I can. And then we go to finally the area of a circle is pi r square, and we get the circumference, which is pi r, two is 2 pi r. And fun fact, this is how they figure out pi. Basically, what they did was, oh yeah, I got the diameter by measuring the circumference, and I'm gonna divide it by 2r or diameter, and that's how they got freaking the number pi. Um, Fun fact, I don't think there's an easier way to get that. I mean, there probably is some like kind of like algebraic shenanigans I can do to get the more concise version. Yeah, probably is. I don't really know how, but yeah. Anyway, next, a circle symbol is that. Central angle is how we will define arc. Arc is a weird bullshit. Some weirdest bullshit you'll ever see because it is defined by a central angle. So it's like a weird skeleton because it's not meters, it's not degrees, it is literally unitless from what I've seen, and it's driving me insane. Honestly, it drove me insane for like a week on how to figuring not a week, sorry. Yes, it was a week because at first I thought it was nothing. Then I keep on going back to it, thinking, what the hell is arc? Arc. And I was thinking, yeah, arc is unitless, isn't it? No, arc is not this because arc I remember it being like a central angle. And how the hell does a central angle what? And then I just realized after a thing that the arc is the curve. Arc length is the measurement of that curve as individually. So that's kind of the headcanon here. And also, I never really tested you on it, but a sector is the area of a circle, and I probably should actually give you a question on that. But yeah, I should, and I didn't do that. Okay. Anyways, we already discussed heavily on these four circle proofs. So I'm just gonna move on to this one because I haven't actually talked about this one. So I should probably make a short on it because shorts actually give more views for some reason, but I'm too lazy to do that. The first triangle we need to bunker up and get is basically this one over here because this one gives you this angle and this angle and this angle and this angle. As you can see, would mean if I get this angle, you just minus OBC with CBA and you get the answer. So that's what kind of that's pretty much what I did, basically. noticing that this is also, oh, let me get a different color because it's gonna bullshit if I don't. This is also, I'm using a mouse also, so give me some break. Anyways, this two will give me this angle basically. And as you know, the same process applies. 1 divided by 2, with parentheses 180, 180 is total angle minus the other angle and the divided 2 because it's isosceles give you the two angles. And that's pretty much it. Anyways, we're trying to get Y, so obviously OBC is first, and then you have to get sorry, no, OBO. So sorry, that's wrong. That's wrong. Sorry. O, no, ABO. I'm losing my mind. ABO like this, and then OBCO, which is this one. And mind my horrible, horrible, horrible artistic quality, and my mic is shit anyways, over here we get this one which is got by isosceles, basically a lot of isosceles, and basically sums up to our second arc right? But this one is from which one? AOB. So this one AOB minus 180, so minusing this to get this huge one. Okay, yeah, so yeah, so that one gave me the big one over here. And this one over here is from these two, which is from this angle, BOC, and then you get this angle. Yeah, okay, yeah, right. And now, as you can see, BOC is the problem because there's no way to get that at first, but then you just have to realize BOC is equal to these two angles, right? And then if that's true, well, this over here is x, so move that along over here, and you get this over here. So when you simplify this, this happens. So you just have to plug in x and then you're done. Basically, ignore the fact that you have an unknown variable and just rope it in. It's kind of what I did. Didn't I? Not really, but you know what I mean. That's needed for this one, but I did explain this. I invoked the half angle theorem shenanigans, but I forgot to actually, explain that. That's why I'm explaining right now. And understand that this is, oh my God, so late. Um, anyway, just understand that. Um, when you look at my short. Anyways, yeah. We did that in a short. A regular polygon can be contained in any because it's an infinite circle's an infinite per regular polygon. So clearly, any regular polygon can just stick in there because it's like a lesser version of it, kind of. Not really, but I don't. It kind of explains it, right? And then we get basically a definition stuff. Basically, this is kind of the thing that I don't remember if it's a Khan Academy or it was in school, but basically they give you like 4 questions and to identify it. I didn't never like that because what's the point of this? I never used them. Um, I mean, kind of used some of them. Maybe I used, yeah. Anyway, if you have any like circle or geometry problems that you think is valuable for me to put here, tell me. I'm happy for suggestions. I don't know. Is it useful for, I don't know, accounting or is it useful for I don't know, electrical? Well, I'll put it in here if it's important for another major, STEM major. So yeah, and then we get to a volume over here. Basic stuff here, like we're gonna yeah, here's some basic stuff, like a surface area, a prism, and I should probably so again, like in the example of a square, a rectangle, the rectangle prism is going to be our standard, basically the way we define everything else. So that's kind of why it's needed, clearly. And then that's further explained when I was doing the pyramid because it just divided by instead of a cube version of it, which is just making the L, W, and H all the same. Um, and I could do more proofs of this, but like getting different prism versions, like if it's necessary, I will. But I don't know how necessary that is. I mean, I already did one of them with a cylinder. I guess I could do a rectangle, like a triangle or something, like a parallelogram prism, but for now I moved on to trig. Well, now trig, I put this question here because it's kind of like kind of like my friend gave me this question to solve because he couldn't solve it, so I just put it in there now. This question is uh basically solve the system, but he couldn't really solve the system, so I did it for him. And it's a fun question. You just make this into a one variable like this, and you're done. Just go through it. Now here is a more hardcore unit circle. Good luck with that one. I don't really like this one because it's so confusing and it makes zero sense. Like what's going on here? But it's all correct from what I found out. I value his input. I value this guy's input, but it's very hard to read. That's what I'll say. Um, yeah, that's it. Although I must say it makes total sense, I think. Yeah, I think. Yeah, it does make sense. Anyways, back to sine and cosine. Um, what happened? So first of all, we do basic like gotcha reviews like that, and then we just graph these. I graph them in this decimals basically and put them in here because like we kind of need to know how they graph, and we're gonna realize that cosine and sine are the same things, just in different relationships. So and they're off. Let me explain like this. If this is like turning like this, the starting position is here, then that would be a sign in our view. That's why the reference point is very important. Because if it started like this in our view, then it would have been cosine. Um, so that's kind of what's happened here. It's kind of like a view shift. Um, and you'll see what I mean when you go down over here. And basically it's a 90-degree shift. So sine is this way and cosine is, it's like a flip. In if you were to make this a reference point, and this is, and I showed that later on, but that's one way to look at it if it's time based. If it's time, this is spatial based, so it kind of a little different. Spatially, it's all depend on reference point basically. It's all depends on reference point, and you can think of it as a wave on a beach oscillating. Um, Spatial units. I don't know. You can figure it out. Vibration. Yeah, vibration. Yeah, vibration. Oh, yeah, that would definitely work. Yeah. Yeah, vibration. Yeah, vibration. Yeah. Membranes and all that. Anyways, more graphs, more graphs, more graphs and how they look. And yeah, I just keep on doing graphs because you never really seen the graphs before and you can analyze it and figure it out. And then we go into let me show you. So imagine a ball and you do a reference point like this, where you start like a ball and you throw and you start it here like this. And your starting point is here, and that would be a sine. If you start over here, it'd be a cosine, basically. And that's kind of how I showed it. Uh, Does that make sense to you? Yeah, it does to make sense to me. Um, does it make it? I don't know. It's something. Um, in reality, is cosine sine. You'll see that later on in physics, but for now, I kind of explain it this way. Um, but hmm, yeah, excuse me. In reality, if it was time, it would be sine, cosine, no, cosine, sine, sine, cosine, sine, cosine, cosine. There'll be an X and Y version. But as you can see, I purposely got rid of all the units, all the X direction, Y direction to make it vague enough for it to work. Uh, But now we're gonna go to the arc sine conundrum, where basically two answers can be given for one, two angles can be correct for one input. So that's basically arc sine, arc cosine, arc tangent. Now here's the thing I look at. So sine basically is the y, basically it's basically y. So when I think of sine, I think of the y changes. So I know that no matter what, those 2 points, so it's gonna look like this. It's gonna go like this direction. Like, let me explain it this. No, 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 no. I keep on doing that mistake. Um, what happened? Where's my algebra? So I think of like this because sine is the y, analogous to y, basically. And cosine is analogous to x. So I just go look like this, right? Now we look at tan, and tan is analogous to both. So I look at this direction. So that's how I see the unit circle, how I see these two questions possible. That's how I see cosine, sine, and tan. You never, I mean, that makes sense, right? That makes total sense. It's already been 30 minutes. Great. Next, we do the addition property. Here's the thing. The addition proof I don't want to look at because it takes forever and you can look at it yourself. And then we go to basically proving that same thing over here where we said, oh, plus 90, well, 120, and you can kind of see, oh, that's a negative version over here. But some of them, like, I don't know which one, 60 over here plus 90 equals 120 over here, which is 120 over here, or well, one half over here. Like, yeah, and then we do some proofs over here, but I think we did it a long time ago, so. I don't need to reprove this, but I know they're correct. I double checked them immensely throughout earlier. Yeah, basically that's how I've been doing. Cleaning and double checking and making sure everything's correct. Yeah, up to now is everything seems correct, so I didn't really and then we went to fact why did I do calculus here? Why? Okay, I might need to move a lot of things. That's for sure. But right now, I'm going to sleep. I'm done. I am done doing my thing. I'm going crazy right now, so I'm going to stop.